Well, now our discussion is regarding the current density and mobility. The current passing per unit area of cross section of the wire is called current density. Or mathematically, we can say the ratio of current to the area of cross section is called current density. Current density is a vector quantity and its direction is in the direction of flow of current. Current density in terms of drift velocity, we have to explain that is the relation between the current density and drift velocity. First of all, we will use a formula J is equal to I over A, where J is the current density, I is current, and A is area of cross section, that is amperes. That is J is equal to I over A. I is the current and A is area of cross section. Now, I can be replaced by a formula that is NEAVD divided by A, and A will cancel off in this equation, and the current density can be estimated by another function that is NEVD. VD stands for drift velocity, N is the number of free electrons, or it is the conduction electrons. E is electronic charge. The formula of drift velocity is generally taken as minus E over m into tau. But being it is a vector quantity, we take the modulus, and modulus of a negative number is always positive. So drift velocity is written in positive expression, that is E over m multiplied by tau. J is equal to NE over m into tau. This expression we got from the expression of J, as it is clear from the expression of J, which is NEAVD. We have computed the value of drift velocity in the equation and we got the value of J, which is calculated as NE square tau over m multiplied by E, where E is supposed to be electric field, but NE square tau over m is supposed to be conductivity. So, for this particular number, NE square tau over m, we can put the value of conductivity, that is sigma. So, J is equal to sigma E. This is another statement of the Ohm's law. We can say that conductivity is defined as current density divided by electric field. So, J is sigma E, or sigma is equal to J over E. The ratio of applied electric field in the conductor to the current density is called resistivity. So, resistivity is given as E over J. One end of the aluminum wire, now we are taking an example to apply the concept conductivity. One end of the aluminum wire, whose diameter is about 2.5 mm, is welded to one end of the copper wire, whose diameter is 2 mm. The composite wire carries a steady current of 6.25 amperes. What is the current density in each wire? So, we are provided with diameters of the two wires, and the composite wire means the combination of the two wires that carries a steady current which is not changing, that is 6.25 amperes. So, we will directly apply the formula, that is J is equal to I over A. Then for I, we can put 6.25 amperes divided by area of cross section. Area of cross section is given as pi r square. R can be replaced by diameter. So the function can be, instead of pi r square, it should be pi d square over 4. So if we compute that value for aluminium, the current density will become 4 into 10 to the power 6 divided by pi. So, we'll calculate this number and this becomes 1.27 amperes per meter square. Now, for copper wire, similar calculation we have to do, and we'll come to the conclusion that the value of J for copper will be 200 amperes per centimeter square. Now, next is we have to apply about the drift velocity, how to find the drift velocity of conduction electrons in a copper wire. So, what we are finding in this question, we have to estimate drift velocity, and if n is equal to 8.5 10 to the power 28 meter cube. we find that drift velocity is J over NE, where J is given, N is also known, and the electronic charge is 1.6 10 to the power minus 19. Now, after computing all these values, we have to make the calculations, and these calculations for drift velocity will become nearly 0.15 millimeters per second. Millimeters can be converted to centimeters or meters. If you divide the number by 10, it will be centimeters, and if you further divide the number, that is by 100, it will become meters. Now, our next discussion is regarding the resistance, the resistivity, and the specific resistance. Normally, resistivity and specific resistance is the same thing. Specific resistance can be represented either by symbol rho or it can be represented by small k. This is the alphabet we can use. So, resistance or resistivity or specific resistance will be rho or simply k. Normally, resistance is defined as the opposition or obstruction to the flow of current caused by atoms and molecules of the conductor. Or otherwise, we have an alternative way of explaining. When current is passed through a conductor, it resists the flow of current. The flow of free electrons due to applied electric field is obstructed by the random motion due to thermal effect and collisions with ions. This property of conductor is called its resistance. The resistance of conductor is equal to the ratio of potential difference across the ends of conductor and the current flowing through it. So we can say that resistance is defined as the obstruction to the flow of current, and this obstruction is caused by atoms and molecules of the conductor. We can't expect a conductor without atoms and molecules. So we can't expect that there is a wire and its resistance is zero. Not possible. So if V is the potential difference across the ends of conductor and I is the current, then resistance of that conductor can be given as voltage over current. The unit of resistance can be taken as ohm, and ohm will be volt over ampere. That is R is equal to V over I. V will be in volts and current will be in amperes. It is represented by symbol that is shown, and that is ohm. If potential difference across the ends of conductor is 1 volt and the current flowing through it is 1 ampere, then the resistance of a conductor is 1 ohm. So 1 ohm is defined as the resistance of that wire which is carrying a current of 1 ampere, and potential difference across the wire will be 1 volt. Normally, the current is also known as sometimes the load on the wire. Now, in the calculations, the CDS conventions are adopted and the value of 1 volt in CDS system is given. So, 1 volt is normally 10 to the power 8 electromagnetic units of potential difference, and 1 ampere is 1 over 10 electromagnetic units of current. So, we can calculate the value of 1 ohm by substituting the values, and it is found to be 10 to the power 9 electromagnetic unit of resistance. The unit of resistance that is given as ohm is equal to volt over ampere. Volt can be joule per coulomb because potential differences work over charge, and ampere is current. So joule, we have to estimate the dimensions. Joule means work done, and work is force into length. So joule is replaced by Newton into meter divided by ampere second. Now we will find that here the value Newton into meter over ampere into second divided by ampere, and this gives the dimension of resistance. The dimension of resistance in terms of mass, length, time and amperes is given as ml2 t minus 3 a minus 2. Now next is our discussion that on what parameters the resistance of conductor depends. Our total discussion is regarding the ohmic resistance, and ohmic resistances are those which obey Ohm's law, that is R is equal to V over I. The resistance of conductor depends upon the length, the area of cross section, the material of the wire and the temperature. We find that in case of ohmic resistances, as the length of the wire is increased or decreased, proportionately the resistance will also increase or decrease. So here we have mentioned that R is proportional to length. If L will decrease, R will also decrease proportionately. If L will increase, R will increase proportionately. The thickness or the area of cross section of the wire. Now, area of cross section means pi r square. R can be replaced by diameter over 2. So, area of cross section can be written as either pi r square or pi d square over 4. Resistance is inversely proportional to the area of cross section. The condition must be that the length of the wire must be constant and material must be constant, the temperature must be constant, then we can verify the B part, that is resistance inverse to area of cross section. The third thing is about the nature of material, that is if we will change the material keeping the length, area of cross section and temperature constant, we will find that the resistance will change. If we consider three different materials like gold, silver and copper, we will find that if their length and area of cross sections are same and being the materials are different, we find that their resistances will differ. The temperature of conductor, that is also concerned with the resistance. We find that resistance of metals or alloy conductors that varies with the variation in temperature. It's a direct variation. Mathematically, we will say that resistance is proportional to L by A, and when we remove the proportionality sign, we write rho, and rho stands for specific resistance or resistivity. Resistivity is calculated according to the above equation, Ra over L. If the conductor is in the form of a wire of radius r, then rho is equal to R into pi r square over L. Basically, it is R A over L and A is replaced by pi r square. We can further change the formula by replacing R, which is D over 2. So, it can be R is D over 2, it is R square, so it is D square over 4. So, pi r square over L can be written in terms of D. D means thickness. The specific resistance of the wire is the resistance of that wire which is 1 meter long and whose area of cross section is 1 meter square. Alternatively, the specific resistance of the material is equal to the resistance of wire of unit length and having unit area of cross section, or the specific resistance of material is equal to the resistance of a cube of unit length when the current flows through the opposite faces of the cube. Specific resistance can be expressed in ohm meter and its dimension can be calculated by putting the dimensions of resistance and meter, that is length. So the net dimension will become ML3 T minus 3 A minus 2. You will remember that all electrical quantities with respect to their dimensions are expressed in terms of mass, length, time and current, that is amperes. The specific resistance depends on the nature of material of conductor and the temperature. So these are the two parameters which decide about the specific resistance. So it is depending upon the material and temperature. It does not depend upon the length and thickness of the conductor. Normally the value of specific resistance of the various substances will be very small in case of conductors, but it is more in semiconductors and maximum in insulators. Specific resistance can also be known as resistivity. It is represented by rho. Now there is an example where we are going to use the concept of resistivity. So our question is, the resistance of a rectangular block of copper whose dimensions are given 2 millimeter into 2 millimeter into 5 meter, where 2 millimeter and 2 millimeter are representing the length and breadth and 5 meter is representing the height of that rectangular block. And the distance between the two faces, that is resistance between the two faces is 0.02 ohms, and we have to estimate the resistivity of copper. So we use directly the formula RA over L. For R we put the value, area of cross section we put by pi r square or pi d square by 4, length is given. So rho is calculated to be 1.6 10 to the power minus 8 ohm meter. Our next example is regarding the two wires, and their materials are same. Materials are same, but the lengths are in the ratio 1:2 and the diameters are in the ratio 2:1. That is the inverse ratio. Lengths 1:2 and diameters 2:1 are connected in series. You will remember that whenever wires are connected in series, current always remains constant. It does not change. So, they are connected in series, and electromotive force of the cell with which they are connected is 2 volt. Internal resistance is 1 ohm. You will further remember that internal resistance is due to electrolyte of that source of current. What is the ratio of potential difference across the two wires? We know that voltage is current into resistance. So for V1, we will write IR1, and for V2, we will write IR2. We take the ratio of V1 and V2, and we will find the expression independent of I, that is R1 over R2. Now, resistance is calculated by KL over A. So, we have to express this expression now in terms of area of cross section and length. So, we know that R is K into L over A. A is replaced by pi r square, and then further we will also write K into L1. That is R1 is R1. That is K L over A, and K will cancel off in the equation. The net equation of V1 over V2 will become L1 over L2 into R2 square by R1 square. And the result of V1 is to V2 will become 1:8. Well, now, two wires of equal length, one of copper and another of manganese, have the same resistances. So we are finding that there are two different materials, but their resistances are same. We have to estimate their thickness. We know that resistance is rho into L over A. Sometimes we write rho, sometimes we write K, but both have got the same significance. So R1 is rho 1, L1 over A1. For manganese, it is R2 is equal to rho 2 into L2 over A1. But L1 is equal to L2 and R1 is equal to R2. Therefore, we come to conclusion that A2 over A1 is rho 2 over rho 1. Now, for manganese, the value of specific resistance is known, 48 into 10 to the power minus 10 ohm meter, and for copper it is also known 1.7 10 to the power minus 8 ohm meter. So we will compute the values. We will find A2 is greater than A1. A2 is greater than A1. The manganese wire is thicker.